Hello, Jerry.
Dennis, how are you?
I'm at home. I'm well.
Very good.
You mean to tell me I'm early for once?
Yeah. Well, the 7 o'clock soft start is meant to be early, right? Oh, others are waiting. Oh, Fred's here. Good. Hello, hello. Everyone is welcome to unmute yourselves if you have something to say during our soft portion of the meeting.
Hi, good to see everybody.
Excuse me?
You guys, I've been missing a lot of meetings because I was going through chemo and then
Oh,
because of
gosh.
chemo brain, but the cancer is gone and now we're just waiting for the brain again.
Oh, awesome. Awesome. Congratulations on clearing out your body there.
Thank you. Greatly appreciate it.
Good evening, Fred.
He must be talking nastier. He would have unmuted himself.
Probably. And I wonder what the big nose implies.
The other day, I was thinking of Dr. Beaker. What is it? Bunsen Honeydew from the Muppets.
Yeah. And Beaker.
Yeah, you were still muted for most of that, Fred, but I didn't realize that I have the power to unmute. I thought I could just ask people to unmute.
Oh, can you hear me now?
Oh, yes. More people coming in. Hi, Olivia.
Hey, Tim.
Hey, Jerry, it's about time you let me in. I've been outside standing in the smoke.
Did you take a deep breath?
I can't even breathe. It's good to be inside. Thank you for.
Rosemary said she's not doing it. Yeah.
Hey, Tim, for Monday night, I'm going to be traveling, but I've got the calendar marked to join in the conversation at 7:30.
Okay, good, Fred. I'll give you a call and then I'll merge Doug in. We can do it just with the conference call like that.
You got my cell phone number?
Let me check. I think I do.
If not, I can just email it to you.
Okay.
Oh, by the way, welcome to the meeting, Don. We're glad you could make it tonight.
Hello, Jerry.
Hi, Olivia. How are you?
Doing just good. I haven't gotten my meeting paper.
Oh, the Valley Skies, the newsletter?
Yeah, Valley Skies newsletter.
Yeah, the printed version is still in the print shop. Sorry.
I guess I'd rather have it sent email.
You'd rather have the emailed version?
Yeah.
Oh,
Yeah.
well, I can change. I can send that easy. We can fix that.
Okay.
I'll explain to him this is your mother's email in case he noticed there's a difference in the
Tim, you appear to be frozen. Now he's
It's
gone,
that cloaking device we were talking about last time.
I guess. There he is.
Jerry, which email did you have? Which email did you have?
Well, let me check real quick. Wolf Shark 2 at Comcast.
Yeah, that's it. Thanks.
Okay.
Okay, great.
As I just announced to the world, you'll be getting a zillion spams now.
Probably, yes. It's okay.
You'll enjoy the company, huh?
Yeah.
Fred, no, I'm sorry, I do not have it. So if you'd send it to me, please.
Yep, I'll take care of that shortly.
So is that an exercise bench behind you, Dennis?
Yeah, it's an inversion platform.
Cool.
I'm not doing it right now. I'm still waiting for the back to get put back together.
Okay. Having some surgery?
Yeah, I had a laminectomy on L4 and 5. Hopefully I will have less pain in my back.
Ah, very good. Oh, pay attention to the waiting room, Jerry. Good evening, Claude. Oh,
He's not,
Claude, you're still muted.
Oh,
There we go.
oh, there we go. Sorry about
There
that.
he is.
It's all right.
I think I have things working now. I just had to jump out of a Zoom meeting for our local astronomy club here in Big Bear. So
Ah,
still getting myself organized.
what kind of club is that?
It's the Big Bear Valley Astronomical Society.
Oh, cool, cool. Very good.
We're a small group here up in Big Bear. I'll talk a little bit more about Big Bear in a bit.
Oh, very good.
you know, who Big Bear is.
How you doing, Claude? I think he's frozen.
Big Bear's down by map down south. Is it down south? Big Bear?
Yeah, the first part of my talk I will show on a map where we are, but we're basically in the mountains just east of San Bernardino.
Okay, I know where Big Bear is. Yeah.
And anybody that's ever been to the RTMC Astronomy Expo, that was held here in Big Bear until, unfortunately, it was canceled last year, but somewhat, I think if it would have been the end of it anyway with the pandemic we're in at the moment. Trying to shut down my other windows here.
Mm.
I used to ski at Big Bear. I mean, ski race.
I'm sorry, what was that?
I was a ski racer at Big Bear
Okay.
in Bear Valley.
Well, greetings to all of you who have joined us tonight, Rochelle and Raymond and Jerry. Trying to say hi to most people when they come in. It's a lot nicer this way. My classes, they come in like 10 and 12 at a time. Oh, Maria's waving. Her camera went up to the ceiling. I just saw a hand. There she is. Thought we lost you, Maria. Thought you went over backwards.
I did. I was talking to my husband.
Uh,
I didn't realize you guys could see me.
Yeah.
yeah, we have other cameras in your house too, you know.
You know what? When I was going through chemo, the kids actually put a camera in my bedroom,
Oh my gosh.
and they would spy on me.
Ah, what's she
Well,
doing
no,
now?
well, they just wanted to make sure I was okay.
Yeah, yeah.
And then they would call me. They would start talking to me because you could speak through it. And they were like, "What are you doing?" I had to go to the bathroom. Are you okay? It's like, do I need to go over there? No, I'm fine.
Ah,
Like a baby queen.
I was blessed enough. They were overprotective.
ah,
We did the same thing when my mother-in-law was living with us. We had well, we called it nanny cam, but,
Right.
and then we also had a baby monitor so we could hear her at night because she tried to get up at night and couldn't do it. So we had to keep tabs on her.
let's see if it's
Yeah,
Captain
that's
Eric
what they
tonight.
did. I actually finished my chemo on March 13th before all this coronavirus stuff went down. They still won't let me drive a car. They won't let me go anywhere by myself. And they pretty much had me in quarantine since September of last year.
Hmm.
What's the cancer of? What's cancer?
I had non-Hodgkin's
Oh,
lymphoma,
wow.
and I was lucky that the cancer that I have, my oncologist told me if you had to pick a cancer, you pick the best one. It's almost 100% treatable. It's not curable, but it's very
All
treatable.
right.
Hmm.
Neat.
And so
That's
I
great.
was able to beat it thankfully. And
That's good.
Well, I'm
And
glad
then-
you got something interesting for us, Eric.
Yeah. Can you breathe inside that thing, Eric?
Eric? Yeah, shouldn't he be driving a Tesla?
Quick question here. I was just trying to test share screen and it looks like that's disabled. I assume.
Well, I will change that now. Go ahead.
Okay.
Yeah.
Uh,
While they're doing that, Fred, you advertised in the newsletter that you're looking for editions of Sky and Telescope.
Yep.
What are you
So-
trying to do? Yeah, go ahead.
I've got Sky and Telescope complete from January 1949 to present, with the exception of 2010, 11, 12, 13, and 14. And I'd like to collect those from anybody who's willing to give them away so I can complete my collection. As a matter of fact, if you look behind me, you can see the white boxes.
Uh-huh.
Those are 1 year, 2 volumes of Sky and Telescope. And behind me starts here. Let's see, where's my finger going? Right here is January 1949. And there's rows of bookshelves that go all the way across, almost completely full now.
Oh, I'd enjoy seeing those sometime. Those older ones, I bet, are really interesting.
Yeah, they really are. Some of the things that we talked about and some of the things that are all historical. It's really kind of interesting to look through. Let me see if I can pull a January 49 out. Hang on.
Yeah.
I used to collect them too, and then the boxes got so bloody heavy I couldn't carry them anywhere.
You still have them, Dennis?
No, I don't even keep them anymore. My thought is to get the DVDs whenever when I get the chance.
Yeah. So Doug Christensen has subscribed to Sky and Telescope for years, and then I've subscribed to Astronomy for years. And so just recently we traded like a year's worth of magazines so I could read something I'd never read before, and likewise he can too.
Something I was considering for our club here in Big Bear was actually having the club invest in the series of DVDs of the history. For a club, for an individual, it's a bit of an investment. But for a club, it's I don't recall what they cost, but it's not that much of an investment. And of course, if you have that into the club's library, it can be shared amongst the club. It's I think that would really be the way to go.
Oh, that's a great suggestion. We might look into it as well.
Because, well, we had to divest of several bookshelves full of magazines, just realized that it just doesn't make sense in the 21st century anymore.
Right. Everything's digital, and it's so much easier to store as well.
Claude, we're getting some extra noise on your microphone. Can you pull that maybe a little farther away from your mouth? Test it.
How is that now?
Oh, that's much better.
Very
Okay.
good.
This is still a fairly new headset to me, so I really wasn't sure if I should be eating the microphone or having it down a bit.
Yeah, we're getting a lot of the breath in there. Very good.
So Fred, you showed us the magazine cover, but can you do that again?
Oh, I just put it away, Tim. I'll dig it out towards the end.
Okay.
It's that was the January 49 issue.
Oh my goodness.
So they're all in pretty good shape. The guy gave me a collection of them years ago, and he had boxed them up, kind of like what we were describing. So I went online to a little company called Uline and found the right box, and they were piled all over the place. So I thought, well, I'm just gonna make it look nice and neat. So my
That's a
kids
great
inherit,
collection.
it'll be their problem.
Well, Bill is the invisible man tonight. Hi, Bill. We see is a bare outline against your background. And Tom,
What happened to Eric?
see you.
Okay.
If you're masked up and ready.
See if I can do this without falling over. Turn it toward yourself, so get better looking. I feel like that. Lean back like that. How's the sound over here? Is
Hello,
it-
Tom Palmer. How you doing?
Can you hear us okay?
Yeah, we can hardly hear you, and that's okay.
That's good.
No, it's pretty quiet, Mike.
Jerry, I didn't know you lived on the lake. That's wonderful. My wife used to live on the lake. Which lake are you on?
Michigan?
Have no idea where that is.
No.
I know. But, no, which way? Whale Lake?
You know, it doesn't have an official name. It's just, you know, like the lake at Spanos Park.
Really?
Yeah.
All right.
I see Bill Lytell has that invisible skin thing going.
Oh,
Can you guys hear me okay? This is Eric.
hello, Eric. We can hear you fine.
I was having some trouble. I couldn't hear anybody.
Eric, are you with us? You look way out there.
He is.
I'm way out there.
Where is he? Oh, that's
I'm surprised there's hardly a delay at all between when your lips move and we hear the sound.
Boy, look how fast the Earth is turning.
So Tim, I just sent you an email. You have the number.
Excellent. Thank you, Fred.
Okay.
Hey, Fred,
Yeah.
do you have anything that you want to mention tonight? I've only got a couple things.
I really don't have anything pressing, Mike. I think,
Okay.
you know, everything we've been hammering out at the board meetings has been going pretty good.
Yeah.
The
Okay.
biggest, number one thing on my list is to introduce Claude.
Okay. Very good. Thanks.
I'm really looking forward to tomorrow night's star party. Or Saturday night's star party.
Still pretty smoky out there.
Yeah, smoke party.
Jeff, we don't look right on that screen. We're at an angle. Is there a gravity thing here?
Yeah, come to think of it, let's just kind of go like that and go like that. Oh, God, I'm good looking.
Yeah, keep the mask on.
Put the mask on.
Let me ask you, Tom, I bet your swimming pool is full of ash by now.
Ash and leaves
Yeah,
from all the wind we've had. Yep. The moon looked like it was a solar eclipse the other day. I mean, lunar eclipse. I'm sorry.
Yeah.
We'll forgive you.
Yeah, I did. Yeah. I took a video of it.
And the sun looks like Mars.
It
Oh,
does.
yeah. Yeah.
Our sky looks like Mars too. The atmosphere in Mars. At least San Francisco did yesterday anyway.
Here, I was thinking it looked a little more like Venus.
Yeah, maybe that.
Even worse.
Hey, Larry, how you doing?
You might not have a sign. Does she have a sign? She's muted, I think.
Larry, turn on your mic and say hi.
Uh-huh.
Let's see if there's a chat thing happening here.
Hi, Jeff.
Hey, how you doing?
You and Mike both.
Yeah.
Nice to hear you.
Hi,
again.
Mike.
Hello.
Oh my gosh, my camera's not on either. Okay, let's go. Here we go. Sorry, guys, my camera wasn't on either.
Oh, okay. Okay.
How are you?
I guess we must be muted.
Are we muted? Nah. How you doing, Larry?
I'm doing good.
Good to see you. Been a long time.
I know it has a very long time. Hey, Mike and Jeff, we got to get our 6 of us together again for another celebratory dinner, don't we?
Yeah.
Do you have any ideas on when or where?
Oh, are you kidding? It's like trying to schedule a Palestinian peace agreement.
Oh, that's good. We could do it at like a park or something.
Well, we can dine outside. There are
Mhm.
places that allow that. I think Bud's and some of those places.
We'll figure it out.
We will. It's great to see everybody, though. It's been so long.
It has
Eric, I'm glad to see you here, still out in space. Good job, buddy.
been. Uh-huh.
Thank you.
Just how far are you out in space? It looks like you're probably about a third of the way to the moon.
That's a Lagrange point, I think.
Okay.
You know, according to your position there, it looks like it's about mid-June. I think there's something not quite right there.
And actually, at the rate in which the Earth is rotating, we're all flying off into space.
Yeah.
It must be him orbiting at super high speed.
Oh, that's probably it. Yeah, good job.
I was going to suggest that, yes.
Hi, Jerry. I haven't seen you in so long.
It's been a long time. Good to see you, Lara.
Thank you.
Dennis, what are you drinking?
Coke, diet.
Ah,
Something to drink or?
Yeah.
Nothing.
Oh,
Okay.
We've got 5 minutes.
I got some of my kids showing up.
Hey, Jeff, have you had any more people recruited for the October program?
You, me, and Bill so far.
Jeff is scheduled for the October program, and then we have someone scheduled for November. We've got programs scheduled now pretty much all the way into spring. So I'm kind of happy about that.
Yes.
Excellent.
I've got 2 people I'm courting for the months of April and May, and possibly one for June, but I don't want to put it out too far because people's schedules change too much. You know, Jeff's talk is next month, and that should be quite an interesting discussion.
Oh, dang. Hi, Mark.
We don't want it. Hey, Doug, I'm not complaining, but we can't see your
There we
face.
Good evening, Becky. That's probably not a
Nice
fake
background.
background, huh?
What's that?
Nice background.
I said Becky's probably isn't a fake background, but you're still muted, Becky. We can't hear you.
Okay. No, I wish I was there, not here.
Oh, okay.
Just look at that clean air. Yeah, I got, there's something we can watch tonight. Is it one of the planets? And I thought, yeah, great. It came on. I can't remember which one it was. Supposed to be able to see tonight, but we're not going to see it, right?
Not tonight.
Yeah, tonight.
Yeah, I went to go for a run yesterday morning, and because I checked, you know, on the airnow.gov, and it said, you know, it wasn't too bad. It was just below 100. But I walked outside and I could smell smoke, and I walked right back in. It says, no, I don't need to run today.
Purple Air is another good site to look for AQI.
Mm. Oh, I am not paying attention here.
You got an angry Bob out there waiting to get in?
Well, I didn't let Mark's wife in, for one thing.
You got a body count of 29.
Oh, Jeff is at Yosemite.
Oh, look at our master show.
Invisible Men.
How did you do that? I don't know.
Yeah.
Something is wrong about that.
I only see two masks in Jeff and Mike's window.
And a pair of
I know, I
glasses,
think
right?
Their complexion is green screening us.
They're invisible men.
Well, look at Bill Lytell, where you see his telescope there. He's right in the middle. You can just see a little bit of that white hair.
Well, I guess the phantom zone isn't going to work.
Hey, Jerry,
Yes.
could you please tell me what the name and the password is to get onto this meeting on my PC? I don't have the mail-in access on the PC.
You want the name and the password?
Yeah, all I've got right now is it on my.
Give me a moment, please.
Okay.
It's format C : /.
There shouldn't be a password, James.
No, it says either enter a meeting ID or a personal link name, and all I have is August SAS and June SAS. And they both have different task numbers.
You can go to a browser and just type in tiny.cc/Stockton Astro.
Hey, James, we got Jerry's email Tuesday at 8:13 p.m. If you check your emails and check for one from Jerry, Tuesday at 8:13, it's got the link right on it.
Okay, the problem is.
Okay, Jim, I've got your information for you.
Okay.
The meeting ID is 923
923
1703
1703
5574.
5574.
Okay, and the passcode is 967 969.
Hold on. The number that I have is 923 1703 5574.
Yes, that's the meeting ID. So how are you talking to us now?
I'm using my cell phone, but the battery's just about to disappear.
Oh, gotcha.
Okay, do not connect, turn on, join. There we go. Password is
Now
what?
you go. I got to look in the waiting room, I suppose, huh?
No,
You are here.
I'm at the meeting password.
Okay.
James is 967
969.
969.
969. Okay. There we go. Join with video. Join. Okay, it looks like I'm on.
Very good.
Let me sign off of this one.
Okay.
Jerry, it's after 7:30. Let's rock and roll.
Started. Jerry, can you hear me or is it?
Barely.
Barely.
Back up, Mike, and see what happens.
Is it better as I back up?
No.
Yeah.
Is it better if I stick my head in the camera?
Slightly.
Let me help.
Okay, I guess we'll wing it. We'll do the best we can. All right, so good evening, everyone. Welcome to the September Stockton Astronomical Society meeting. And I think you all know me, but my name is Michael Berry, the current president. And I do have a couple messages that I just want to talk about, or things to talk about real quick before we start with our guest speaker. One is elections are coming up. It's going to come up through the newsletter, but just to let everyone know, a heads up, Jeff, and he's the head of the nomination committee, and then I'm drawing a blank.
Tim Cycling, Amelia Cycling, and Christy Abbott.
Thank you. Yeah, so you can contact any of them if you want to run or if you want to nominate someone. This would be a good time during this, the end of this, towards the end of the month and everything, so we can have some viable candidates. The other one too is I want to mention that in October, the dues are due. So hopefully many of us can go ahead. I'm just getting ready to pay my dues, and hopefully we can get most of this done so we don't have to go coercing everyone to pay those dues. Okay. So anyway, this evening, Fred, as always, has gotten some wonderful lectures. It looks like this one's going to be another winner. Just a great one. So Fred, I'll let you go ahead and introduce Claude, and we can't wait to hear him.
Okay, very good. Thanks, Mike. We're really privileged tonight to have Claude Plymate from the Big Bear Solar Observatory, and he's going to talk about the observatory and the good, I believe it's pronounced good, solar telescope. We were talking earlier in the meeting is if anybody had gone to the Riverside Telescope Makers Conference in Southern California, you'll know where this is. And if you're driving to or from the conference, the observatory is right almost smack on the water, essentially on the water. And it's pretty impressive to see. I've read a number of articles about the telescope and the equipment and some of the experiments and research they're doing there. So it's a very interesting place. Claude Plymate holds a master's degree in astronomy and has spent the last 34 years working in the field of solar astronomy. From 1986 to 2011, Claude worked for the National Solar Observatory at the McMath Pierce Solar Telescope in several capacities, including telescope site manager and engineering physicist. Claude left the NSO in 2011 to accept his current position as chief observer and telescope engineer at the Big Bear Solar Observatory. Now, just a couple of comments is, if you've ever been to Kitt Peak, you know about the McMath Solar Telescope. It is a giant telescope. It's unfortunately, it's been decommissioned, but years ago I had the privilege of going there and visiting, and it was very, very interesting. The other thing I learned about Claude just about I guess about a month ago, is he and I went to cross town high schools. He went to Encinal High School in Alameda, and I went to Alameda High School in Alameda.
Yeah, I was from the wrong side of the tracks.
Yeah, something like that. So with that, ladies and gentlemen, I'm going to turn it over to our guest speaker, Claude Plymate. Thanks, Claude.
Well, thank you very much for that, and thank you for having me. These are difficult times, and we're doing what we can to keep coming together and keep educating ourselves. So thank you very much. I'll try to keep this somewhat brief. Let me see if I can share my screen. And Yes, I think you're seeing my presentation now, which I've titled the Goody Solar Telescope, Big Bear Solar Observatory, the highest resolution solar telescope, which actually was true for the first, let's see, about 11 years of its existence. But just last December, the National Solar Observatory, my ex-employer, finally got first light on their 4-meter solar telescope, 2.5 times the size of our telescope here. So now I have to modify this talk and say that we now have to reconcile ourselves to second place, highest resolution solar telescope in existence. As already been discussed a bit, several of you do not know where Big Bear Solar Observatory is, so I'll give a quick tour. Maybe zooming in would be a bit more helpful here. Can you see
Claude?
Yeah.
We're still getting a little bit of that buffeting noise from your microphone.
If I send it down further, is that better?
I believe so. Thank you.
Okay, let me know if this audio is okay. If not, I'll just go without the headset and see if my internal microphone works. Can you see my cursor, by the way?
Yes.
Okay. This is a map of Southern California, the Los Angeles basin down here. And here in the San Bernardino Mountains, just about an equilateral triangle from Mount Wilson to our northwest and Palomar down here is Big Bear Lake. Let me zoom in. Then right there in the middle of the mountains is the lake. Zoom in further and you'll see this causeway, 1,000-foot extension out into the lake. That is the Big Bear Solar Observatory. The dome is at the end of that causeway, actually out in the lake. So, of course, you might ask, why Big Bear Lake? Well, back in the 1960s, Caltech wanted to develop a world-class solar observatory. They already had Mount Wilson, they had Palomar. They wanted to move into solar astronomy. So the Southern California mountains are already well known for very good stable seeing. And Southern California also has rather good weather statistics. On top of that, though, of course, we are observing during the day where ground heating becomes a problem. I spent 26 years at the McMath telescope on Kitt Peak, and one major problem is observing during the day, the ground gets hot, you build those thermals up around your telescope, and that destroys your astronomical seeing. Since we're all astronomers here, I will be using some jargon. If I need to stop and define a term, just please let me know. But Bob Blayton, an astronomer at Caltech, had an idea that the water of a lake would hold down the daytime heating around the solar telescope and suppress those daytime thermals and preserve the natural seeing that the site has. Interestingly, people, of course, ask me, well, is the telescope used at night or can it be used at night? And unfortunately, no, it is not. It is a purpose-built solar telescope, but also the conditions of the lake, which tends to be colder than the daytime ambient temperature and holding down that thermal. At nighttime, here at 2,000 meters, 7,000 feet roughly, the nighttime sky cools very quickly, and that situation reverses to where the lake becomes a thermal source for us. So the good seeing is actually destroyed at night. A site survey was conducted, and Big Bear Lake was found to be a near ideal site for development. And Professor Hal Zuren at Caltech was the one who really pushed through development and was named the first director of Big Bear Solar Observatory back in 1969. First light telescopes in 69 were two twin 10-inch refractors. That's well before my time, so I can't say much about them. I did find these two photographs. Obviously, the two refractors were housed inside of a common spar with later apparently a third refractor. I think this was called the Singer telescope, I think I've heard, mounted in this common spar. And I do recognize these two Leo filters on the back end, but that's about all I can tell you about it. So let's move on. Those telescopes did not last very long. In 1972, a 26-inch solar telescope that was built to fly on Skylab 2 became available. You've never heard of Skylab 2, and there's a good reason. It never flew, it was never funded, but the telescope was developed. So Hal Zuren somehow convinced NASA that, gee, maybe they should test that telescope at Big Bear. So here is a picture of the telescope that went into operation in 1972. The entire telescope was mounted inside of a vacuum chamber to hold down internal scene in the telescope, and mounted on that same poor mount and pier that previously held two 10-inch telescopes. Plus, they ended up mounting a couple of extra refractors down below it, so that was one overloaded mount. Once the telescope was decommissioned in 2007, it was donated to the Los Angeles Astronomical Society, and a couple years ago, I accepted to give a talk to them back when we could actually meet face to face. And I got to, they pulled it out for me and I got to visit it at, I think it's still in the same location here at the Griffith Observatory. So why New Jersey Institute of Technology? At the time I was working for the National Solar Observatory, I'd never even heard of NJIT. Well, in 1997, Zuren decided to retire. And at that time, Caltech was investing very heavily in nighttime astronomy, developing the twin 10-meter Keck telescopes on Mauna Kea, Hawaii. So they took that opportunity to divest of both of their solar facilities, which included Big Bear Solar Observatory and the Owens Valley Radio Solar Array in Eastern California. A request for proposal was issued for operation of BBSO, and the winning proposal was written by New Jersey Institute of Technology, NJIT. It turns out that that's not as strange of a fit to BBSO as one would think, because several of the astronomers at the NJIT Center for Solar Terrestrial Research did their PhDs at Caltech, so they were well familiar with the facility and its potential. The one who really pushed through that proposal and the concept was Dr. Phil Goody. And so being the one who spearheaded it, he was named first NJIT director. Okay, here's our alphabet soup. We are the Big Bear Solar Observatory. We are now a remote laboratory for the Center for Solar Terrestrial Research at New Jersey Institute of Technology. So why a new telescope? Well, when Phil Goody took over in 1997, we were approaching the 21st century. That 26-inch telescope had been quite a workhorse. It had been in operation since 1972. But by the end of the 20th century, there were new telescopes in the works. First of all, the Japanese were planning to launch a 0.5 meter solar telescope into orbit called Hinode, which eventually was launched in 2006. And the National Solar Observatory was in the early part of planning to build a giant 4-meter solar telescope, which has now been named the Daniel K. Inouye Solar Telescope, or Daniel K. Inouye Telescope. No, Solar Telescope, that's correct. We all call it DKIST, and it just recently saw first light last December. So in that environment, Phil's problem was, how could BBSO continue to be competitive and relevant? Well, he knew he had to think of a new telescope and had to think big. The question is, of course, how big? Well, we all know, we're astronomers, size matters. Come on, guys, let's face it. Bigger is always better. And of course, larger aperture, you can collect more photons. That's, of course, secondary to solar astronomy, but aperture also equates to resolving power. Larger aperture, I should say for a given wavelength, results in higher resolving power. And if you plot, here I've plotted the resolving power, fixed wavelength right in the middle of the visible spectrum at I always pick half micron, 500 nanometers as a convenient wavelength. So here's the curve you get as aperture gets larger in the x-axis here. Of course, the resolving power, the angle you can resolve on the sky, continues to get smaller. You're already at resolving 1 arc second at an 1/8 of a meter telescope, about a 5-inch telescope. You pass half arc second resolution at a 1/4 meter, that's 20 inches, down to a 1/4 arc second, half meter, et cetera, et cetera, et cetera. Unfortunately, the atmosphere limits our ultimate resolving power here on the ground, on the Earth's surface. Even at about the best sites in the world, you're going to be limited to about a half arc second of resolving power, no matter how large your aperture is. So here we are coming to larger aperture, and beyond this half arc second cutoff, you're not getting better resolution due to the Earth's atmosphere. It's no coincidence, therefore, that those first telescopes at Big Bear were 10-inch telescopes. You can see why. So what to do? Of course, there is perfect seeing in space, but space is incredibly expensive. The rule of thumb I always hear is space telescopes are about 3 orders of magnitude the cost of the equivalent ground-based. So take a typical $1 million telescope. You want to launch that into orbit, that's $1 billion telescope. That's just untenable. And here's a cartoon that, of course, shows the situation here. We have a space telescope that has absolutely perfect seam. But in the last 100 kilometers, that perfect seam, that flat wavefront, passes through our atmosphere, which is always in turbulent motion, is jumbled up and blurs our image. What to do? Well, the answer came in the form of adaptive optics. Adaptive optics was conceived of back in the 1950s. I think Babcock and somebody else I don't remember were the ones who actually conceived of it out at Mount Wilson, but it was not possible to really develop with the electronics available in the 1950s. Starting around sometime in the early 80s, the Department of Defense started in secret developing the concept. They had interest in being able to image satellites from Earth's surface, etc. And so a lot of those that were working on adaptive optics and became successful at it were astronomers, and they lobbied heavily to be able to at least declassify some of the information. They were given that permission in the late 80s, and that was disseminated into the astronomical community. And since then, just about every large telescope in existence is either has adaptive optics or is developing adaptive optics for their telescope. And in a nutshell, we have a cartoon showing you have this nice flat plane wave coming through the atmosphere. It gets distorted into some random shape, and that distorted wavefront falls onto a mirror that is controllable by computer to create the appropriate wave, the appropriate shape to cancel that wavefront distortion, resulting in getting that flat wavefront back and restoring the diffraction limit image of that telescope. Part of that image is picked off to some optics known as a wavefront sensor, which can show what the distortion of that wavefront is. A computer then analyzes that and decides what voltages need to be sent back to the actuators on the back of that deformable mirror, sometimes called a rubber mirror, to cancel the residual wavefront error. Now, I'd love to go into a lot of detail about adaptive optics, but unfortunately that's another talk in itself. And in the interest of time, I'll move on, except to say that a properly designed and implemented adaptive optics bench can restore the diffraction limit image of a telescope, i.e. as good as in space, but over the caveat that it only works over in one point on the sky. That correction will fall off very quickly. Think about the fact that if you're correcting the wavefront distortion from this point on the sky, well, a wavefront coming from off axis will pass through a different part of the atmosphere and have a different distortion. So the corrected area can fall off very quickly. And when I say quickly, I mean several arc seconds. So here is the deformable mirror we use here at Big Bear. It's a 100mm diameter, about a millimeter thick mirror with 357 piezo actuators on the backside, and you can see this bundle of wires down below that. That's each wire goes to a separate actuator that's adhered to the back of this mirror to be able to push and pull on that mirror. So here is a movie. Hopefully it's not too choppy. It's of course smooth on my side, but I don't know how badly it comes over the internet. But this is a fairly typical bad scene day at Big Bear. But once you turn on adaptive optics, this is what you would expect to get, which is, of course, a dramatic improvement. But we are not done yet. The way we take data is we take a burst of mini frames. In this instrument, in the case of this instrument, we take 100 frames very quickly over a few seconds, reject the porous scene quality 30, retain the 70, and then in post-processing use a technique known as speckle reconstruction to pull out the highest resolving elements across the image. And this is a movie that we would be left with on a typical day. And even I still find this just awesome to look at, the detail in there. This is roughly 40 arc seconds across, I believe that is. And we're looking at, half-hour data probably. So again, how big is big enough? Well, any telescope that was developed had to be able to, for logistical reasons, fit into the existing facility that was already built. Also, keep in mind the sun does not have a solid surface. It is gaseous. So features at some level are going to be nebulous. There is going to be a limit to the spatial structure, the spatial scale structure on the surface of the sun. And theory tells us that's going to be somewhere in the ballpark of 50-ish kilometers. Some people say maybe down around 20, some people say a bit more, but somewhere in that ballpark, which is 0.07 arc seconds resolution to achieve 50 kilometers resolving power on the surface of the sun. For, again, in the middle of the visible, that insinuates at least a 1.5 meter aperture to be able to resolve that spatial scale. Also, the telescope being built here in Big Bear was designed to be and justified and partially funded as a pathfinder / technology demonstrator for that 4-meter telescope being developed by the National Solar Observatory, the 4-meter Daniel K. Inouye Solar Telescope, DKIST. And as I said earlier, DKIST finally achieved its first light just this past December. Okay, let's do a quick virtual tour for those of you who have not been to Big Bear before. Here is the north shore of the lake, and Highway 38 comes along the north side of the lake. A smaller road, North Shore Lane, splits off from that, comes down, and right here is the Big Bear Solar Observatory. To the north side of the road is our main facilities campus, and then to the south is that 1,000-foot causeway with the dome at the very end of the causeway. So the first thing you would see when you pull in, turn to the right, you come into our parking lot. Here is our main facility building, which includes a director's residence on the right, administration office, machine shop. There's another building behind with numerous offices, 5 dorm rooms, meeting hall, kitchen, garage. And then not shown off to the right is what's officially called the Hartley Solar Lab, but most of us just call it the barn. The off directly to my right from this photograph is a caretaker's facility. One of our scientific programmers and his wife live there. It's called the Mud Cottage. Then across the street, looking due south, you look straight down towards the telescope. And along that causeway, there are a few other smaller facilities. We have one of the field sites for the National Solar Observatory's Global Oscillation Network Group. It is a series of 6 small telescopes placed around the world that monitor the sun basically continuously for looking at solar oscillations to do solar seismology. Again, I'd love to say more about it, but we best move on. Moving down the causeway, before you get to the main dome, there is a smaller dome, which is, for historical reasons, called the Hartley Earthshine Dome, but now
Claude, excuse me, we lost your audio.
Whoops. Okay, sorry, I bumped my switch here. I assume I'm back now.
Yes.
And where did I leave off?
Historical reasons for the HL.
Okay, it was originally called the Hartley Earthshine Dome, but now it's only used for full disk H-alpha imaging through the day. It's just a commercially available. I bought it from Edmund Scientific, a 100 millimeter refracting doublet to the f15. But what is special about it is the filter. It uses a very exquisitely good quarter angstrom wide Leo filter. It was built back in the 1960s for NASA. There were several of these distributed around the world at that time, and we still have one. It is a superb H-alpha filter. So here's a typical data product that comes off of it. It's mostly used, again, as a patrol telescope so that we can watch the disk continuously to see in real time if there's eruptive phenomena that we could use as targets of interest for the main telescope. Moving on to the main dome, the Goody Solar Telescope. So the first thing you would do is enter through the front door. I'm sorry, OSHA, there's only one door in and one door out. So we live with it. Through this door, there's a small patio area that's enclosed that has a compressor and a few other items now. And then just a few feet beyond that door, there's another door that then enters in, oops, wrong way, enters into the first floor interior. So if you come in through this door here, the first floor has just 3 offices on it. My office on the right, an electronics lab in the center, and a visiting astronomer's lab or office on the left, east side, and a bathroom. So then turn around, go through this door, up 2 flights of stairs. Through the door that you come to, turn to the right. There's a small room here you pass through, then go through another room, and that brings you into our observing room. Now, this is our optical engineer, Nicholas. He was operating the telescope the day that I snapped these pictures for you. And you can see that we are following COVID-19 protocol. Whenever we come into contact with each other, we keep our distance and we wear our masks, etc. Observing room, we have many terminals set up. Over on the far side of the room is mostly science camera. The monitors in front of Nicholas right there are for telescope control, and we also have a GUI for controlling the small dome. Out the windows here, you're looking directly north down the causeway. Then we have several other monitors just off screen for adaptive optics control, several webcams that are monitoring the telescope itself. We try not to spend any more time in the dome than we have to. Of course, our excuse is we don't want our body heat to destroy the scene. The reality is it can be bloody cold up there in the winter. So standing where I was, if I turn right around, and there's another door behind us, and that looks into our electronics computer room for we have our telescope control electronics control computer and a couple of our archive servers, etc. in that room. It has 2 air conditioners now to maintain a comfortable environment in there. I should also mention that it's adaptive optics control computer and electronics in there. So it generates a lot of heat. We found that it was overheating. We just recently got a second air conditioning unit in there, and that's now keeping up with it. Now, if I back up again, turn back out through this door, go out through the hallway that we're in, instead of turning to my left, if I turn to the right, there's another door that takes us into our Coude lab. And it's difficult to show our Coude lab. It's very cramped in there. We keep in mind this telescope, this observatory was originally built around 2 10-inch telescopes, and it has grown now to a 1.6 meter telescope. So space is at a premium. We have optics benches that are mounted vertically on the wall next to the telescope pier. which holds most of our adaptive optics, optical train, one of our high-speed CCDs. We have stacked horizontal benches. Over here we have some Fabry-Perot interferometers. This channel here that I'm circling. This is a Fabry-Perot interferometer for scanning the H-alpha line. Over on the far side, we have stacked Fabry-Perots, etalons, for scanning infrared lines. Down below, this is our near-infrared array camera, and I don't expect that all this makes a lot of sense to you, but hopefully it'll become a little more clear as we go on through the talk. Go back out, continue up the stairwell up to the 3rd floor here. On the 3rd floor, this was originally the telescope dome floor. However, with the new telescope, the telescope pier here in the middle of the room had to be extended upward to lift the telescope higher. And so this became a, well, when I arrived, it was basically just storage, but we repurposed it into an infrared coude lab. This large instrument here is a all cryogenic spectropolarimeter. It's a cryogenically cooled spectrograph that has all the optics at cryogenic temperature, the work environment, the diffraction grating, collimator, reimaging mirror, etc., are all servoed at 90 Kelvin, 90 degrees C above absolute zero. And the infrared array in there is kept at 30 C above absolute zero, 30 Kelvin. We have the light from the telescope comes in vertically on the far side of the telescope here. It's kind of hard to show, where we have several optical benches for the 4 optics. I show just a little bit of it here. This is the input aperture, input window into the instrument, the cryostat. We have several optics for reimaging, polarization optics, an image scanner. On this floor for the infrared, we do not, as of yet, have adaptive optics, but this small bench up here is an image stabilizer, a fast tip tilt mirror. Then come around, one more flight of stairs. You're at 7,000 feet. I hope you're keeping up with me. You finally come to this telescope floor itself, and this is the Goody Solar Telescope. So let's talk a little bit about the telescope and its development. The primary mirror, as you all know, half of an observatory expense and effort is the primary mirror. And in our case, that's no different. The primary mirror started out as, well, the University of Arizona. I assume you've all heard of the Giant Magellan Telescope, a instrument, one of these new giant telescopes being developed down in the Atacama Desert of Chile that is utilizing 7 8.4 meter mirrors in a multi-mirror arrangement. Now, these 8.4 meter mirrors all have to work together to form the shape of a single parabola, meaning the center mirror is a typical symmetric parabola, but those mirrors around the side are extremely off-axis telescopes. You can't just take a parabola and tip it on its side. You don't have you have a very aberrated telescope at that point. What you have to do is actually polish in that segment of the parabola into that mirror. That had never been done on such a large optic before, and particularly that far off axis. So the University of Arizona wanted to develop a demonstrator mirror before they tackled a full 8.4 meter mirror. Phil Goody somehow cut a deal with the University of Arizona to split development costs. The University of Arizona got to develop the process for polishing, figuring, and testing such an off-axis mirror. And when they were done, BBSO got the mirror. So our telescope is really designed around that mirror. And that also means that the Big Bear 1.6 meter primary is a 1/5 scale model of a GMT mirror. Now, anybody that's good with math will quickly tell me 5 times 1.6 does not come to 8.4 meters. It actually comes to 8 meters. But our mirror is actually physically a 1.7 meter mirror. However, it is so far off axis that it projects an elliptical profile. So we stop it down to a circular 1.6 meter clear aperture. Here we have an optical diagram of the telescope. The primary mirror is a daughter segment of an imaginary 5.3 meter parent parabola. Imagine taking a 17.5 foot mirror and cookie cuttering out one side of it. That's not, of course, how it was made, but you can imagine that is what we have. The mirror itself is made of ultra-low expansion Zuritter, and this results in an unobstructed, all-reflecting optical system. So we don't have any secondary or support structure in the beam, so that for us that avoids diffraction, which would damage our image quality, both in resolution and in contrast. The way to imagine that is think about your typical Newtonian image with those nice diffraction spikes. And who doesn't love diffraction spikes? They're beautiful. And who cares if you're looking at a point source, the star, that it kind of actually helps you to find where the star is, where X marks the spot. But on an extended object like the sun, every resolving element across the image would have diffraction spikes, and that would create a haze, decreasing both our resolution and our contrast. And while the sun is a very bright object, it is actually a rather low contrast object. Also, being an all reflective system, that allows us to utilize the telescope both for visual and infrared observations. Now, a lot of people, a lot of you astronomers are going to be surprised to hear that we do not have a Cassegrain optical system or Ritchie-Chrétien, anything like that. We actually utilize a Gregorian optical system. Now, a lot of you are scratching your heads going, but I've always heard a Gregorian is an inferior optical system. And the problem with a Gregorian is it is not a wide field telescope. First of all, this is a solar telescope. We're looking at a very small segment of the sun. We are not a wide field telescope. So here's a simple diagram, a cartoon of a typical Cassegrain telescope with your parabolic primary, which then starts to bring the conical light in towards the focal plane back here, but you have your concave, and in the case of a Cassegrain, I believe it's a hyperboloidal secondary, which slows the optical beam and forms an image plane back somewhere further down the optical train. Here's a Gregorian, and in a solar telescope like ours, we go with a Gregorian design for a very good reason. It gives us access to that primary focus. So again, same parabolic primary, you have the converging beam down to your primary focus, then a diverging beam back to a concave, actually elliptical secondary mirror, which then sends the beam back to its, I use the incorrect term, but I will continue to use it here. I still call it a Cassegrain focus. Now, the reason for having the Gregorian is we want access to that primary focus. Now we have a 1.6 meter diameter mirror. 1.6 meters is approximately 2 square meters of surface area, 2 square meters of collecting surface, looking at the sun. Now, the solar constant you've probably heard of is about at the Earth diameter, at the Earth distance from the sun, we're radiated with roughly 1.36 kilowatts per square meter of energy from the sun. There'll be some loss through the atmosphere, but I figure at the Earth's surface, we're still getting irradiated with about 1 kilowatt per square meter. We're collecting up 2 square meters, so we're collecting 2 kilowatts of power and concentrating that down into a 36 millimeter diameter primary image, 1.4 inches. 2 kilowatts in that kind of area. That's enough energy that it will melt metal. So the way we handle that, oh, here's another diagram showing that with the optical diagram, the off-axis parabola, we form the, we have access to that primary image ahead of the secondary mirror. And we can manipulate that without infringing, without obstructing our beam. Now, the way we deal with that is at that primary image, we have a highly reflective, just aluminum surface. It's actually a hollow aluminum cavity through which we constantly circulate a water glycol coolant to keep it from melting down. In the center of that, that polished aluminum surface, we have a 3 arc-minute aperture. So here is a frame grab I did of a web camera I have mounted on the side of the telescope, looking up at that heat stop that I use to monitor the position of the sun. And I should have actually had the sun. This is showing that the sun, the telescope right now is pointed right at this center. You can see that 3 arc-minute aperture. I probably should have done it when we are not right at this center to show you that it's not always there, that the disk moves around, but I didn't think of that till just earlier today. Now, 3 arc minutes, that's about 1/10 the solar disk. So we are reflecting away almost all that 2 kilowatts of power, and we're just reflecting that away. It diverges and actually scatters off the side of the dome and doesn't bother us. And we are passing only about 1/100th of the total energy. So only about 20 watts of power going on down to our secondary mirror. Keep in mind, we are not de-resolving the telescope. This is a field stop, not an aperture stop. So over those 3 arc minutes, we still have the full brightness and all the resolving power of the telescope. We just are limiting our field down to a maximum of 3 arc minutes. And then beyond our image plane here is our elliptical. Again, it's an off-axis elliptical. This one actually was physically cookie cuttered out of a larger elliptical optic, which gives us a backup mirror. So, and then on down. Other modifications, the original 30-foot hemispherical dome had to be swapped out for a 34-meter maximum diameter 5/8 sphere. And now you might see why we had to, well, I wasn't part of the observatory at the time, why the telescope here had to be built up higher so that the telescopes could be set up higher to where it matched with the maximum diameter of this dome. And that just gave enough space to shoehorn that telescope into the dome. And this is a modified radar dome. Yes, it looks like a radar dome, and that's because it is. And being fiberglass, it is a fairly lightweight dome, etc. The mount itself is a commercial mount from DFM Engineering up in Colorado. It's a modification of their standard 50-inch telescope mount. It is an equatorial mount okay, it is an equatorial mount, and the way the optics work, we do send the beam straight down through our polar axle, meaning that as the telescope rotates through the day, that beam goes straight down through the polar axle, does not move. It does rotate, but it does not move. And then just a couple of mirrors allows us to send that beam down to our 2 coude labs, that infrared lab 1 floor down, or which we pick off the mirror for, or typically send the beam straight down to our main coude lab down 2 floors. And this, you can see, are our stacked optical benches, the adaptive optics bench mounted vertically on the wall there. Okay, here's another image of our number 2 mirror, that off-axis elliptical. The heat stop is here. Water lines, you can sort of see them coming in from the back there. Our number 2 mirror is mounted on a hexapod. 6 struts that come up that are all adjustable. That gives us 6 degrees of freedom that we use to compensate for flexure and mirror. As the mirror warms up through the day, the focus will travel on it. So the 6 axes, let's see, we have X, Y, Z, tip, tilt, and rotation. So we can control all those. And for an off-axis telescope, collimation is even more important than in a symmetrical telescope, because not only do we have to keep the number 2 mirror at the center of the actual optical axis of the telescope, and but we also have to maintain the relative rotation between the primary and the secondary. So flexure can be a problem, but we tune that up several times through the day, and the adaptive optics can take care of the rest. Now our primary mirror cell, here's looking at the back of the telescope, is a 36-point passive flotation cell. The way it works, and this is an idea that goes way back. I think it was originated all the way back with Mount Wilson. But we have 36 little levers. The mirror is supported on 36 points on these levers, with each one of these square blocks you see is a 5-pound weight. Now, the weights are adjusted back and forth on that lever to where the mirror is just supported properly. So the right amount of force just to float the mirror, we call it. Now, the brilliance of this design is that, of course, as the mirror goes off to the side, the amount of force necessary to support it changes. The gravitational vector is now pointed down that way, so you would need less force to support it. If you had the same force, you'd just be shoving that mirror out. But using this lever system, as the mirror tips to a different axis on the sky, the counterweight rotates, or that weight rotates the same amount, and the same gravitational vector shift on it. So it automatically compensates and keeps just the right amount of force onto the mirror. Now, it was originally thought that we would probably need active optics as well as passive optics. And you see all these holes on the back of the mirror cell. Those are designed to mount each one of those a electric actuator to back up that lever system. But the telescope was put into operation, and it was found it worked well in passive mode, so the active optics were never implemented. Now, again, this is a solar telescope. We are not looking over the entire celestial sphere. We're only looking over the declination range that the sun moves through through the seasons, from plus 23.5 degrees down to minus 23.5 degrees. So we don't have to have a telescope that can rotate anywhere on the sky. And I'll get back to that. I think I should say a few other words first before I get back to that. Here you can see our mirror cell, and if you look carefully, you can actually see how wedged that mirror cell is to point off to the side. The light comes in off of the primary and comes way off here to the side, where our heat stop resides here at the top of this A-frame structure, and our elliptical secondary up here, which brings the beam down to a tertiary mirror here on the side of the telescope, which then sends the beam through our declination bearing to a fourth mirror, which sends the beam down through the equatorial axle. Now note, that means our declination bearing is way down here. On a typical fork equatorial, you'd expect that declination bearing to be up here in the center of mass of the telescope. But due to the off-axis nature, it had to be way down here, which means that there's an incredible amount of mass hanging off one side of that declination bearing. Well, of course, you would think, well, the obvious answer is add a long tangent arm out here with a big counterweight. The problem is, keep in mind that, first of all, we don't have room in this dome. We barely have room for the telescope. Secondarily, this pier was originally designed around those 10-inch telescopes. It simply can't handle more weight than we are already running on it. So we just were not able to counterbalance the telescope. So instead, the idea that was come up with, and I believe that this was DFM that came up with this idea, 2 servo motors run screw jacks that push against 2 pistons that compress springs. The springs, we know the spring constant. We can measure the how much the spring is compressed by some small linear encoders. Sorry, senior moment there. 2 linear encoders measure how much we compress the springs. We know the declination of the telescope, so we can work out how much force the spring has to support. And so the computer takes care of that. As we move in declination, these, what we call the force motors, are constantly compensating to keep enough tension on that spring so it supports the telescope. Then over here, there is a second screw jack that works as our declination drive. And since we don't have to cover the entire sky, just a small segment of it, 47 degrees, that screw jack gives us enough range to cover that region. Now, a lot of you will probably recognize these tubes on the side, what I call the tusks, and as counterweights, and that's exactly what they are. However, typically on telescopes, once the telescope is balanced, you move the counterweights to the right place and they are left until something is changed on the telescope. Again, due to the odd off-axis and asymmetric structure of this telescope, those counterweights have to move as the telescope moves in declination. So as we slew north, there's 2 600-pound counterweights that have to move up and or down the tube to keep the telescope balanced in that axis. So the telescope, let's see, that 26-inch Skylab 2 telescope went into operation in 1972. It was removed in 2007. So it was a workhorse at Big Bear for 35 years. It had quite a good run. Then first light for what it was at the time called the New Solar Telescope, NST, was just the next year, May 2008. Phil Goody ended up retiring in 2013. And so in 2017, we had a ceremony we rededicated the telescope in his honor. So the telescope is now known as the Goody Solar Telescope, GST. And here's a picture of a nice plaque that was fixed to the side of the telescope here up in the dome. Now here's what I refer to as the proof of the pudding image. Here's a very early image taken at Big Bear simultaneously with an image taken by that half-meter Hinode Space Solar Telescope. It's the same field, same frame, and you can, if you look across there, there's one-to-one correspondence between the features. However, clearly demonstrated that, at least at that time, Big Bear was able to outperform any telescope in space or earthbound for solar observations. It also demonstrated that we were able to achieve diffraction limited images with that telescope. However, now jump forward 11 years, and that 4-meter DKIST telescope announced first light in December of 1919, just last year, several months ago. And here is the same scale comparison, same image, very early image here at Big Bear. Keep in mind, since then, we have improved on several things. We have a newer generation adaptive optics system, better post-processing, etc. But here is their image taken with their 4-meter. And you might be surprised to note that, you know, the image, we're not completely blown out of the water by the difference. But that, if you think about it, is to be expected. Because remember I said that there is a smallest physical scale on the sun. And what this tells us is that we really are running up against that limit in the visible. Okay, here's a side-by-side comparison, a shootout between the Goody Solar Telescope and DKIST. Excuse me, I think I'm really supposed to officially call it the Daniel K. Inouye Solar Telescope. We are a 1.6 meter f2.4 meter off-axis Gregorian. There are 4 meter f2 off-axis Gregorian. We are an equatorial mount, which keeps things simple. However, to keep costs under control and to have a reasonably sized dome, they went with an altazimuth mount. Their resolving power, again, right in the middle of visible, we should theoretically hit 57 kilometers, and we do. We can do a little better than that if we go blue of that, but this is a convenient wavelength. DKIST, well, they should be down at 23 kilometers resolution on the solar surface at that same wavelength. Again, what that probably means is that they're running up against actually seeing the finest scale structure there is on the sun. What I find truly interesting is out at 1.5 microns, where there's a very important, astrophysically important iron line. Our resolution is down to about 170 kilometers, where they're still 68 kilometers. They're almost matching the resolution we can get in the middle of the visible out at 3 times that wavelength. And I think this starts to show you the obvious collaboration potential between these 2 telescopes. Out at 5 microns, where I did some of my work, we're all the way down to 570 kilometers. They're 228 kilometers. Our first light, 2008, first light DKIST 2019. Unfortunately, right after that, something called COVID-19 hit. They were planning to take about 3 months after that December first light before they went into online for science observations. However, of course, things have been delayed due to the pandemic. I heard a rumor, all right, there was in a meeting yesterday, I heard the latest schedule is they're hoping to be online this coming April for science observations. Our heat stop passes 3 arc minutes 3 arc minute field of view, reflecting about 2 kilowatts of power. They have a field of view on their heat stop of 5 arc minutes, so a larger field, and that is an absorbing heat stop that must absorb more than 12 kilowatts. That is a true engineering challenge. And there were some difficulties with that, but I am told they now have that worked out. Our Coudet lab is a simple fixed Coudet lab with a field rotation, since we're an equatorial telescope, 15 degrees per hour set rate. Being that they are an altazimuth telescope, they have a varying rate of field rotation, and they rotate the entire Coudet lab. So kind of a merry-go-round arrangement that has to vary speed to match their image rotation rate. We have a full suite of visible IR imaging and spectral polarimetry instruments, including multi-conjugate adaptive optics. Their first generation instruments are heavily based on our instruments, one-to-one correspondence between them. Here is a big difference. We're at about 2,000 meters elevation, around 7,000 feet. They are at 3,000 meters elevation. Now, we are low enough in the atmosphere that there is still a lot of water vapor above us. We are not a coronal site. We have too much scatter in our atmosphere to be able to observe the corona. They should be high enough, at least in the infrared, to be able to do direct observations of the corona. So that's a big difference. Development costs, 25 million for the GST over about 5 years. DKIST, the official number is 344 million over about 20 years. Our operations budget, about 1 million per year. Their operations budget, about 18 million per year. Now that is as much as I was going to say about other telescopes, but just last week, the German telescope, Gregor, announced that they are just coming back online after a 6 months downtime for upgrades to their optics, mechanical, and electronics to allow the best possible imaging quality they can get. Gregor is a 1.5 meter, so just ever so slightly smaller than our mirror. They're on in the Canary Islands, Tenerife, at slightly higher than we are, 2390 meters. They also have a high order adaptive optics system. They are operated through now I hope nobody here speaks German because I will obliterate my pronunciation, the Kiepenheuer Institute for Sonnenphysics. We all just call it KISS, the German Solar Astrophysics Group. The real difference is that while DKIST and GST are unobstructed off-axis telescopes, Gregor is an on-axis telescope, which is probably a much more rigid structure, and engineering-wise is a much simpler structure to deal with. But they do, of course, have a support structure for their heat stop and their number 2 mirror, which will result in diffraction, and so due to that, they'll never be able to quite match our resolving power here at BBSO, but they will be close. And here I made another quick comparison, that same image I keep showing from the GST versus the image that they released. And yeah, again, they look very, very similar. Unfortunately, if you look very closely at this, there are a lot of artifacts from processing and some fringing in there. The expectation is they still have probably some alignment work to do before this telescope really is fully performing to its theoretical possible. And so I'm hopeful over the next year that they will improve quite dramatically. But they needed to put something out, so this was just last week. Move along. Okay, and I mentioned, again, adaptive optics. And I said that it corrects over 1 point on the sky and can fall off very quickly. There is a new concept called multi-conjugate adaptive optics that will be truly necessary for the 4-meter solar telescope DKIS to be able to utilize that much aperture. Their corrected area would be just too small to be truly useful. So the first test bed, MCAO, multi-conjugate adaptive optics, has been a joint development project between BBSO and the National Solar Observatory for DKIS. And originally, Gregor was also part of that, but they ran out of money and dropped out of that several years ago. So it continues to be a joint project between BBSO and NJIT. And I'm not going to say much about MCAO except to say that by using multiple deformable mirrors, correcting for different layers in the Earth's atmosphere, you don't get a better correction, but that the correction you get applies over a wider field. And let me restart this video. So here, come on, start, there we go. Here you have what's now being called classic adaptive optics, and you can see it's maybe only a few arc seconds across that corrected area before it falls off. Switch to multi-conjugate adaptive optics, and you can see now that that correction applies almost out to the edge of our field. And this is about a 70 arc second field out there. Moving on. Now, here is the actual movie that first image I kept showing you was taken from, and this just was to demonstrate early on that the telescope not only could achieve diffraction limit, but could achieve that over an extended period through the observing day. We don't look just at the photosphere, of course. We also look at the chromosphere. Here is an H-alpha centerline image taken with our Fabry-Perot, and you can see that the H-alpha structure nicely traces out the magnetic field lines up in the chromosphere. Now here, I hope this comes across nicely. As far as I know, this is the finest H-alpha centerline movie ever produced. And you can see a lot of features going on everywhere you look. I wish I had time to talk at length about this. You can see that it's being corrected for our image rotation. I got to show this at least one more time. You can see umbral oscillations down in the center of the sunspot, which are propagating up along the into the chromosphere here. Structure falling in along the field lines there. Just an incredible image or movie. I'm still in awe of that. Now, using a Fabry-Perot is very similar to an Etalon, like you would get from Janet Daystar or Coronado, that sort of thing. Except being a solid Etalon, it uses two separated plates, which are controlled through piezoelectrics that allows us to scan, change the wavelength very, very quickly and scan through the H-alpha line. When I say quickly, I mean on the order of milliseconds. So here we are coming through making a movie as we are off axis. As you're out, once you come through the center line here, you're looking high up, the most opaque part of the H-alpha line. Come out the other side, you're looking deeper and deeper into the chromosphere and then all the way down to eventually to the photosphere. The features you do see are those, when you're off band, are those that are Doppler shifted. On the red side of the line, which we're coming in over here, that's material that is falling in, red shifted, so onto this line, onto this part of the line. Over in the blue, these features are features that are being ejected outward from the sun coming radially towards us. So here's a quick movie just showing a red wing of the H alpha line with material falling in towards that sunspot. Another, here's just a pretty image. I'm proud of this. This is a demonstration image I made from some of our data. Another thing you can do with scanning that line very quickly and keeping the image stable with adaptive optics, you can combine an image from the red wing along with an image from the blue wing and the center line and create a Dopplergram. I've done that here, colorizing the red wing, obviously red, the blue wing, blue, I'm not very creative, and the center yellow. So you can actually see in the color the velocity in this image. And it just came out really, really pretty. I'm really proud of that image. Also, we have another instrument, our near-infrared imaging spectrometer. How am I doing on time? I guess I'm eating up time pretty badly. I better move along. Our near-infrared imaging spectrometer, NIRIS, can produce what are known as magnetic maps, magnetograms, by looking at the polarization of the line and how the line splits, a phenomenon called the Zeeman effect, which I won't go into. But by analyzing the polarization, we're able to determine the strength and polarization of the magnetic field on the surface. So here we have the intensity gram in the infrared, just what you think of as a normal image. And here you see the different polarization. Here is one magnetic polarity, the other. The other data product that NIRIS can produce is looking at a helium line that's formed at the very, very top of the chromosphere, right up near the transition region. So it's a good proxy for what's actually happening in the lower corona. It is much less optically dense than H alpha, so the field lines you see are these nice, very thin tendrils, and you're seeing down all the way to the down to the photosphere. But several years ago, with that instrument, looking in the 10830, we were able to catch this very nice flare. So you can see the magnetic orientation traced out by these field lines coming up, and then at some point the flare occurs, bang, there it goes, and you can see how the magnetic field has reconnected and simplified after that. Moving back to the photosphere with our broadband filter imager, which is just a fast CCD camera looking at the photosphere. Here's a few years ago when we used to get sunspots. Remember those days? Here's a beautiful light bridge going across, which in this image is clearly not a bridge over the top of the umbra, but convection flowing up through. You can see these motions in the penumbra. Everywhere you look, there are things happening. Small bright points that are moving inside the umbra, etc. Another spectacular image. Now, in November of last year, we had the Mercury transit across the disk. We were able to lock onto Mercury with our adaptive optics, and then had to hand guide to follow that across the sun. Here's one frame. Unfortunately, our post-processing, our speckle reconstruction, doesn't know how to handle high contrast objects very well. So when we go to the movie here, you will see some features from that. Particularly when we get to the limb, yeah, there's several strange features that show up from the post-processing, but that was a fun experiment, and we were able to get some science out of that. Plus, it just was fortuitous that the size of the disk fit well into our wavefront sensor. Maybe I'll just skip over these two quick movies to in the interest of time, and just let me finish with this. I like to finish with this image. It's not by far the finest image we've ever made, but is one I made. It's not that great a scene, but I just think it's a spectacular, pretty sunspot with that, which I call it the bumblebee. And before we go, I'll say a couple words about Big Bear Solar Observatory during this pandemic. We were shut down for about 4 weeks, 4 or 5 weeks. But since then, we have restarted science observations. Our procedure allows only a single staff member in the dome at a time. Of course, during this, public tours are not possible. And well, tours will resume someday. All I can suggest is that keep tabs on our webpage. So thank you very much. And if there's any questions, if we have time for questions, I'm happy to entertain a couple.
Well, that was a great presentation. Thank you very much. We have a couple of questions came in, but they were really good straight person type questions. That question led just ahead of the answer that you gave during your presentation.
That's
so
always a good question when you know the people are going. I keep having to say, that's the next slide. That's the next slide. Just hold on.
We have a number of members that are telescope makers, myself being one. So the optomechanical aspects of the Gregorian telescope versus the Cassegrain and the Coude focus were very interesting. I know you had mentioned to correct for field rotation, the systems on, I think you used the term merry-go-round, that tracks.
But that was my term. That's not an official NSO term.
No, that's okay. I totally get it. But I mean, is the whole optical bench rotate? Is that how that works?
The entire room rotates.
Oh my word.
Yes, it is a very expensive, the entire platform rotates around the telescope pier. It is huge. I don't remember the diameter, but it is quite an operation. I haven't actually physically seen that. I haven't been out to Hawaii to see it, but for us, it was far simpler just to go with plop down an optical bench and say, okay, you have field rotation. Deal with it in software.
Nice. Okay, so we do have a question comes in. This is from Tim Clark. And Tim asks, does the BBSO have the benefit of the inversion layers and steady air similar to nearby Mount Wilson Observatory?
Yeah, the seeing is, we have very good seeing here, as is most Southern California mountains. Just like Mount Wilson, again, this was originally developed by Caltech, the Mount Wilson observatories. So just like Mount Wilson, Palomar, Big Bear Mountain is the first mountain range that intercepts that laminar flow off the Pacific. We do rely on the typical westerly flow that, so we have very good natural astronomical seeing. The point of the lake is to maintain that good astronomical seeing through the day. Unfortunately, occasionally we do get the Santa Ana winds where the wind reverses and comes out of the east. And instead of having this nice pristine laminar flow off the Pacific, we're getting air that comes in off the Mojave Desert that tends to already be a bit churned up. So during that, our seeing tends to be much poorer. The worst seeing for us is when the wind comes out of the north, because there's a mountain ridge just north of the telescope, and so we're in the leeward side of that burbling air mass there.
Absolutely. So,
and also, maybe I should mention also, our mirror cell was originally, originally being designed to carry active optics, was also originally designed to hold an air handling manifold system that would constantly flush the mirror cell to remove hot air out of there and break it out through the bottom. To their great surprise, when they first opened, got first light, they found that the telescope actually worked without that air handling system. Later, some hydrodynamic studies figured out why, and that was due to the fact that the mirror is canted, the mirror is heating up, and the natural convection tends to pull that hot plume up. Plus, we have all those louvers on the side of the dome, which are opened up, and we allow that westerly wind to come through the dome and flush the mirror cell. So we rely on about 1 meter per second flow through the dome to actually flush that air out of the mirror cell.
That's an interesting point. We have 2 more questions have come in. I want to go back to one of them, and it had to do exactly with what you're talking about. Is does the air surrounding the instrument, when it warms up, does it cause heat waves that pass through the optical path, causing any kind of disturbance?
Now, if you look at our dome, you'll notice that it's not a typical dome. First of all, it's a 5/8 sphere and not a hemispherical dome, but also it doesn't just have a slit that opens. What we have is a circular aperture, we call it the iris, that moves in front of the telescope across the sky and pulls a sunscreen up along with it. So the only sunlight we allow into the telescope is hitting, first of all, that the field stop, or the aperture stop that stops us down to a 1.6 meter, and then onto the mirror. The rest of the dome is always in shade. So that, with the flushing of the air, the dome interior is pretty much at ambient temperature. So no, we really don't have much dome seeing.
Okay. So there's a couple more questions come in. This one's a little more politically motivated. Several years ago, the NSF was reprioritizing observatory funding, and the BBS was at risk. Is this true?
Up until COVID-19, Big Bear our budget was in rather good shape. And I know about how budgetary requirements, that's really why I'm no longer with the McMath Pierce Solar Telescope. That defunded, and I needed to find fresh blood. It was an easy recruit when they brought us out here. So we have not only our base funding through the university, through NJIT, but we also have several grants with NASA, and we have a contract with the Chinese. So up until the beginning of the COVID-19, we were in really rather good funding shape. Now that the university is in trouble, we are doing fine at the moment with carryover funds, but if this pandemic goes another year, that could start to be a problem. Let's see, we have contracts with the NASA to give an idea of what we do besides our own research is we have a contract with NASA to support the Parker Solar Probe. As you know, that's the satellite that's in orbit, a very elliptical orbit around the sun. And what is it, about 3 times per year, it swings in for a perihelion and takes all its data at that point and then swings back out again to cool off. So we have a contract with NASA to supply support observations, 30 days either side of their perihelion. We also have a contract to supply 1 month per year data to the Chinese Chinese National Observatory. And we are also partners with South Korea. So we are doing fairly well now, but in 2020, I do not make predictions about the future.
Okay, very good. Now, there's a couple other questions come in. I want to pop one in because being a former telescope maker myself, the one ray trace that you did showed off-axis of one of the segments of the mirror, and I think it was for the Magellan telescope, where the center is essentially the center part of a parabola.
I
And
think that was, I think the optical diagram you're talking about is actually our telescope.
okay, maybe it was. What went through my mind is because of the focus is off axis, what came through my mind was it reminded me of a Schiefspiegler, where a Schiefspiegler is an off axis type mirror, but I think the optical system is completely spherical.
Yes, and so that's why you have to have all that that secondary optic in there to correct for the I thought it was pronounced Schiefspiegler, but yeah, you have a very strange secondary mirror and then yet another optic which corrects the aberration from there. But that is, as I recall, it is a spherical mirror that's been tipped, and the advantage of that is, of course, a sphere does not have an optical axis, where a parabola does. And as far as that optical diagram you're talking about, it really doesn't matter whether you're looking at the at GMT or our mirror, because it is a model of that mirror. And so we are extremely off axis, and that's not necessarily by our design. That is due to the fact that you have to, it is designed to be able to fit yet another mirror in the center of that optical axis, with our mirror off to the sides. It really is a GMT model mirror.
Got it, got it. Okay, here's another one back to the optical path in the Goody telescope itself is the heat diverter by the secondary mirror dumps heat. Does that go into the optical path?
No.
Or is that absorbed by the cooling system?
Neither. We have that to reflect, we have that heat stop at the primary focus. It's tipped off to the side. Of course, being that it's just bare aluminum, I polish it by hand. It's not meant to be an optical surface. It's just a reflective surface. So it's just a polished metal flat with water behind it. It will absorb some heat. What bare aluminum, that's probably 4% of that goes into the water and carried off to chillers off there. But the rest of it is just reflected off. Now, keep in mind that we have an f2.4 beam. So beyond that image on the heat stop, you have a quickly expanding beam that's again, that heat stop is tipped off to the side, so that is reflected away from the telescope and just scatters off the side of the dome.
Okay, got it.
For 2 kilowatts, that was acceptable, and the beam, once it hits the side of the dome, is larger than, it's a couple meters across, so it's actually larger than our primary mirror. So the intensity, the flux in that scattered beam off the side of the dome is lower than ambient light. DKIST, however, with 12 kilowatts, they had a very complex absorbing heat stop to try to carry that heat away. It's a much more complicated, much bigger problem.
Yeah, 12 kilowatts in a small area is a lot of heat to dissipate. Another question came in about the Goody telescope is, can you describe the coating on the primary mirror and mirror segments, or is it unaluminized?
Yeah, I can describe it very simply. It's aluminum.
It is aluminum coating.
We do not overcoat. It is bare aluminum. And like most large telescopes, we do that because occasionally we need to recoat. We have recoated the mirror twice now. And as a matter of fact, when I was hired in 2011, they needed to quickly get me here from Kip Peak so I could be I could be involved in the process of removing the mirror here, getting it on our truck and driving it back to Kip Peak so it could be coated in the 4-meter telescope chamber there. So for simplicity, on large telescopes like this, you just go with uncoated aluminum, and because when you go to strip it off, you want to make sure that you don't have a problem getting that overcoating off.
Exactly, exactly. Very good. Okay, any other questions? It looks like the hit list here is slowing down a little bit. I think our speaker is slowing down a little bit too. All right. Claude, this was an amazing presentation.
Well, thank you very much. I
really
appreciate
enjoyed this. I'm glad we hooked up. With that, Mike, I'll turn it over to you.
Yeah, okay, thank you. All right. Well, that pretty much concludes what we have here. If anyone has anything to talk about tonight, go ahead and bring it up. Oh, and Jeff has to make an announcement here for our raffle.
All right, so at our meeting, we've been having a selection of a winner, and tonight's winner is, drum roll. There you go. Becky Greider, are you still here? I don't see her. Oh, doggone, too bad, Becky. Where did she go?
I think it was up.
So Becky Greider won a Starbucks card. So she's here. I'll get it to her. I don't know where she went. Congratulations, Becky.
All right.
Excellent presentation, Claude. Really enjoyed it. We'll look forward to going down for a tour when you resume giving tours.
Yeah, let me make one comment on that. Tours will resume someday, but it may not be me involved. I am trying to retire right now. I was actually supposed to be retired. I had announced 2 years ago I was retiring on Labor Day 2020. Well, due to the pandemic and the university implemented hiring freezes, we've not been able to hire a position for me to train yet. So I've currently agreed to stay through the end of the calendar year. But after that, I'm going back to putting some leather patches on my sleeves and being a gentleman amateur astronomer in my backyard.
Good for you.
Good for you.
That was outstanding. Thank you very much. That was as good as any we've had this year. Excellent.
Yeah,
I also
it was
want
really
to say
enjoyable.
that I like your cat. I'm also a cat lover. So,
Thank you very much. I appreciate that.
All right, Mike.
Okay, that's basically it, folks. I'll call the meeting over. If anyone wants to continue speaking, that's perfectly okay, but officially it's over. Thank you.
Yeah, I'd just like to say, this is James.
Okay, thank you.
When NeoWise was up last month, it was really quite good from my backyard. I had a nice view of the air. I was able to see the split in the tail, but the contrast was pretty poor because I was down so low. But you know, it was pretty visible without having to go up the hill.
Well, I just want to jump in real quick and say thanks. Go Jets, you know, from years ago. And I hope to talk to you again soon. I have to get ready, get some sleep before I go to work tomorrow. Take care. Good night, everybody.
Good one.
Thank you, Fred.
Good night, Fred.
Right.
Thanks, Jerry. Thanks, Fred.
Thank you all, folks.
All right.
Do we still have a machinist in our organization?
Oh,
Fred.
do we have one in our club?
Yeah. Do we?
I use Mike Scooter in Tracy.
I might be wrong, but I think Steve Clark is something of a machinist.
That's right. Yeah, he had a machine shop. He might still have a garage machine shop available.
Yeah, I think I remember him offering his services to the group.
Well, I've got an
That's
18
awesome.
millimeter aluminum plate here that I'd like shaped.
Nice horns, by the way, James.
Oh yeah, here's the sun. There's the moon up near the top.
Oh.
Well, if you keep your head in the right place, it just gives you a nice set of horns. There you go.
Yeah, well, it also gives me a little bit of a halo there, kind of a glow behind. And
very good.
Hey, I'm looking at Eric's picture. I can see us coming into view right now.
Here, I'll give myself some horns.
Oh, okay, good.
There we go.
It looks more like
Up just a little higher.
It looks more like a crown.
Well, it's supposed. It's Thor's helmet, so.
Nice.
Hey, Eric, do your glasses fog up inside that helmet?
Nope.
That's pretty cool, Eric. I like that one.
Yeah, mine is actually a lake at the South Pole, and that's about the only place on Earth you can get water, the sun, mountains, and the moon all in one picture.
My image isn't being created through the Zoom background feature. It's I'm creating it through the free open source OBS software. Jeff is familiar with OBS software. That's what he uses to, I think, make his videos for his kids on his YouTube channel. But it's just a series of overlays. I've got the video background of the Earth, and then I have an image of the astronaut overlaid on top of that, and then I have another video capture overlay on top of the astronaut with my face masked to a small circle. So and then I just pipe the video. I just pipe the video from OBS into Zoom as like a virtual camera.
So with my OBS, I can do that?
You could, yeah.
I'm gonna try that.
I'm thinking if you could like wave a gloved hand, in the image, that would be awesome.
I'll have to work on that one.
Getting too fancy.
Can you see that there's like a little reflection on my glass though?
Oh yeah.
Yeah, isn't that cool?
How'd you do that?
My video is set with a opacity level. So the image of the astronaut, here I'll show you. I'll show you without my video. The image of the astronaut already has a reflection on it. And then my video, I'm just have like a 40 or 50% opacity on my video. I thought it was pretty cool.
Cool.
Very nice. Hey, we're all getting bigger.
Just real quick. I was curious, how many people were watching, well, of those remaining now, how many were watching the video, the shared content with the side-by-side view of the gallery?
Oh, no.
Oh, I was. Yeah.
Because I had about 3 or 4 people on the right-hand side.
Yeah.
Yeah.
Called speaker view.
Okay.
Well, because I wanted to mention, if you go up to the very top when someone is sharing content.
I do see that up there.
There is a view options up there.
You just click it and then you saw.
Oh yeah.
Gallery view gets the gallery.
And you could turn off the side-by-side mode and pop out the gallery view like a different screen if you want. And then there's also the option up there to like fit the video to the screen. And you can zoom in too. There's like a zoom option where you can, if you're having trouble reading the content, you can up the zoom level to whatever you want and then pan the image around.
Oh yeah. Never noticed that up there. Can you guys hear me, by the way?
Yes.
Oh yeah.
Okay.
So I had used pin video to the speaker, and so I got a large image in the middle of his screen that he was showing, And then just a view of him off to the side on the sidebar. I didn't see anyone else.
Yeah, that's another choice. I forget how to do that, but I tend to get out of it because
If
I like to
you
see.
right click on somebody's image, you can do just hit pin video, it comes up.
Chat pin video.
Yeah.
You guys, I have an Australian mode. Have you seen my Australian mode? This is my Australian mode.
Ah, there you go. But the pin video mode should be good for the recording.
I forget where I read it. Oh, I think it was in Sky and Telescope magazine. Somebody is reporting that we're supposedly already in the extended corona on the outside of the Andromeda galaxy. We're already starting the process of the galaxies colliding.
Dang.
Hey, can I show you something? Can I show you guys this eyepiece here?
Okay.
See the razor I got in there?
Oh, hey, cool.
That's my Phobos and Deimos tool.
Oh, no.
It's awesome.
I'm sorry, can I
Now
see it
if you
again?
Get the damn smoke out of here. I'll try it.
Ridiculous.
So
Can I see it again, Jeff?
2 years ago when we had our Mars opposition, I was flat on my back looking at the ceiling and couldn't move. Thinking, all right, I got it this year. Smoke.
I think October is supposed to be the best viewing of Mars for this year.
Which means the rains will clear the smoke out somewhere around January.
Yeah, right.
Mm. Well, I can tell you that I was up in Tuolumne Meadows and beyond for the entire last week. And the smoke basically stops right there at the meadows, just about at the crest of the Sierras, and did not extend over the other side down towards Mono. So it was perfectly clear on the other side.
I wonder how White Mountain is.
It's high. It's very high. I think the smoke wouldn't make it up. Well, I don't know, actually. It might. There's the big Fresno fire, so.
Well, I tried this on an 8mm eyepiece, and the tube was way in. I had to put the razor way inside the tube. So I found this 32, and I was able to put it right at the aperture focus there. So what I'm going to do is I'm going to put my 5-power Barlow on there and try that. But I think I'm going to get Phobos and Deimos if I can just get the clouds for the smoke to go away.
That's cool.
They're the only 2 moons I'm missing.
Mm.
Yeah, that's awesome.
Did you get all 80 plus of Jupiter yet?
No, well, I'm talking about my 20 moons. I can see 7 on Saturn, 4 on Jupiter, 1 for Earth, 5 for Uranus, 1 for Neptune. That's 18 moons. I want to get 2 more. Phobos and Deimos. I've never seen them.
And 20 gets you a certificate? What's the deal?
No, but we can make a club certificate, I'm sure. But I just know I can get 20 moons. And
Okay. I see. Personal goal.
Yeah, that's right. We'll have to make a club certificate for 20 moons.
Oh, there you go.
Oh, cool. Yeah, I'm trying to get a new, see if I could share that real quick. I've got a new telescope that I picked up. It was Rick Zarica's telescope. How do I show? Oh, yes. And I'm just getting that set up, but just like you, I'm just dealing with, let's see if I can show that. Let's see.
How did you get his scope?
So there it is. So it's an Orion Eon APO triplet, 130 millimeters. It's a little bit bigger than my other scope, and it has not seen first light yet. So, hopefully that will be coming about pretty quick. But I have it all set to go. I have everything installed.
How did you get the scope?
Oh, that was at Rick's had an estate sale. He passed away. He was a friend of ours from way back in the day, and back in the 70s. And his wife was selling off all his gear, and so I was able to pick up this scope. Very happy to have it.
I heard somebody died, but I didn't know it was him.
Yeah. Mm-hmm. Yeah, a little while back.
Yeah.
I hadn't actually seen Rick in many years. Fred kept up with him pretty well, but Just like I hadn't seen Fred in many years. I hadn't really seen Rick either, but it was nice to see a lot of the old friends from back in the Chabot days, and yeah. But I'm just hoping my mount will handle it. It's actually a fairly heavy rig, right? The way it's set up. I had to add that black counterweight, and I've got them all the way out. So we'll see. I don't know if it's going to track well or not, but we'll find out as soon as it clears up.
Oh yeah, I just got my Orion mount also working again. The power cable, the head of it snapped off.
Okay.
And I had to send away for it because they don't stock it. And it took them like 2.5 months to get it in from China for a $15 cable.
That's annoying.
Yeah.
What
Well,
telescope do you mount on that?
Right now, I've got 2 of them mounted. I've got an 80 millimeter Apo, an Acro, not an Apo, an Acro, on one side, and on the other side, I've got a C5.
Oh yeah, that's nice.
It right now it's hooked, set up for alt-azimuth, but it's basically a equatorial German.
Bye, guys.
All righty. Good night, Jeff.
Good night,
I'm going to do
everyone.
the same, folks.
Yeah, me too.
Nice seeing you all.
Hey,
Talk again soon.
James, just real quick, James.
Yeah.
The thing that you need machined, does it need to be on a lathe or does it just need to be cut out?
It can be done on a milling machine. The plate is basically a 12 by 12 inch plate, 3/4 of an inch thick. And what I'm trying to do is replace, you know, the telescope I've been trying to build. I'm replacing the bottom plate with a machined aluminum one rather than trying to do it in plywood.
Okay. Is it something you think can be done on a CNC machine?
Yes. I'm just trying to figure out, I'm just trying to figure out which CNC machine I should get to do it.
Well, I haven't used it yet, but I just purchased that handheld Shaper Origin CNC.
Oh, the one that Jerry, there he is, told me about 9 months ago or so. You put little tags down and
Yeah. So if you want, we could try it, but if you would, but I've never used it, so I'd want to practice first on some scrap wood or something.
I've got plywood here you can practice on. Okay. I tried to cut it all by hand, and I think I've done a fairly decent job of it, but it's just, you know, I can't dig out areas that I want to dig out to cut down on weight because aluminum's somewhat heavier than the plywood. Okay. But it's also stronger too.
Okay. Well, we'll talk about it offline so Jerry can get off.
Fantastic. Sounds good.
Good night, guys. Good night, James, Eric.
Good night, everyone.
Okay.
See you later.
Very
Bye.
good.
Good night.
Yeah.
Where is the button? Oh, settings. Oh, there it is. Leave. Good night.
Good night, James.